Now that we have a good understanding of differential forms in R3, in particular the 0 forms, 1 forms, 2 forms, and 3 forms, we're going to go ahead and see how to rectify that with our integration of vector fields and how we can build a theory of integrating forms instead, and then relate that to our integration of vector fields. So let's recall we've already done this for 1 forms. So we did line integrals of 1 form fields. So how did we do this? We said if we let w say be or omega be p dx plus q dy plus r dz. Here p, q, and r are functions of x, y, and z. And we let c be a curve given by, say, some parameterization r of t for t between a and b. Then we define the integral over c of our 1 form field omega to just be the integral from a to b of omega. And remember, we wrote omega sub r of t, but we're thinking of the r of t as a point. So this becomes then a 1 form, and then we evaluate this at the vector r prime of t dt. Okay, so here, recall, we think this part here is we're abusing notation and viewing this as a point. And then this part here, this becomes a differential 1 form. So if you remember differential 1 forms, this is our inputs vector, so this is our input vector. And then once we do that, that differential 1 form spits out a scalar. So this is just a regular Calc 1 or Calc 2 style integral of one variable. So we saw that already. So our next step is to look at integrating 2 forms. And remember 2 forms, so 2 form fields here. In 2 form fields, remember our 2 forms gave us area, so we're going to want to integrate these over surfaces. So let's go ahead and take an easy case of this to start. So let's start just in R2. Okay. So in this case, there's not a whole lot of 2 form fields. So in this case, we could write omega as f of xy dx wedge dy for some function f of xy. And so maybe you just want to check that dy wedge dz and dz wedge dx are 0 when restricted to the xy plane. So that's not hard to see. Maybe just go ahead and check that to make sure you understand why this type of 2 form is our only 2 form field if we're working in just the xy plane. Okay, so let's let S be a region in the xy plane. Okay, and omega as we just defined. Okay, so the f of xy dx wedge dy. So what we'll define then, there's not a whole lot of possible ways to define this. Well, this should be the integral over s, and then my omega, of course, is just f of xy dx wedge dy. And then we want to think about, well, what is dx wedge dy? Well, remember when we input vectors into that, we're just looking at the area of the parallelogram spanned by those vectors. So dx wedge dy is just an area here. So we might as well define this to just be the integral over s of f of xy dA. So of course this could possible ways to write this. The dA we know is dx dy, or we could also write it as dy dx. And so this is just a normal two-dimensional integral in the plane. One thing to keep track of here, to be a little careful of, is notice this area form here. This is a signed area form. So remember, that gives it an orientation. So that orientation, so dx wedge dy has orientation. And what was that orientation given by? We used our basis of R2 to be ij. So if we think of this in terms of our normal vector, so if we think of S is actually inside of R3, so it happens to be just a flat surface inside of R3, then our normal vector is k hat, which is what we're used to. And that's because of choosing our orientation to be ij, so normal vector is I cross j. We could, of course, we could look at omega being f of xy dy wedge dx, but then that would just introduce a negative sign everywhere, and our orientation would be in terms of j comma I, and we get negative k for our normal vector. So just to make sure we remember how this is working, let's just go ahead and work an example and see that this works exactly like just taking regular two-dimensional integrals in the plane earlier. So our two-form field here is x squared y dx wedge dy, and S is going to be the surface given by, let's just go ahead and draw this out. So we're going to go from 1 to 1, and let's look at this area. This region in here is going to be our S. So then our definition says that the integral over S of omega is the integral over S. Well, we have this as x squared y dx wedge dy, which is the integral over S of x squared y dA. And now we're back in the situation of when we did integrals, when we first started doing integrals in the plane. So we can choose dy dx or dx dy, whichever we prefer. So let's just say we go from 0 to 1 and 0 to 1 minus x of x squared y dy wedge dx. So we're fixing an x value and we're seeing what our y values are. So we're doing this, we enter here, and we exit here. This line, of course, is y equals 1 minus x. So that's where our limits come from. And now this is just a simple integral to evaluate. So first we do the dy. So I have a 1/2 y squared evaluated from 0 to 1 minus x dx left over. And if we go ahead and simplify this out a bit, this becomes 1/2 x squared minus x cubed plus 1/2 x to the 4th dx. And then if we evaluate this, this is just 1/6 minus 1/4 plus 1/10. So nothing new here. This is just really just a simple, it's just a rewriting of what we've already done. And it isn't even much different in terms of how we write it. So we want to move on to general surfaces, but before that, let's take a look at Green's theorem and see what this says in terms of what we've done. Okay, so we have this new language. Let's see what Green's theorem would say. So we had a couple of ways of writing Green's theorem before. So we could say, if we let f be pxyi plus qxyj, and let's say S is a bounded region in R2 with boundary curve. So sometimes we'll write boundary curve like this with a little delta S. Let's go ahead and call this C. So then one way we wrote Green's theorem was that the integral over C of pxy dx plus qxy dy is equal to the integral over S of q, partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. In another way we wrote this in terms of the vectors, vector fields was f dot dr was the integral over S of the curl of f dotted with k dA. So those were the two versions of Green's theorem from before. Right, so when we just did in terms of vectors, we wrote them that way. So now let's rewrite this. So first, we see we already have a 1 form showing up here. So let's let omega be this 1 form. Now let's go ahead and calculate the derivative of this. So if I do d omega, remember this is dp wedge dx plus dq wedge dy. And if we write out what this is delta p delta x dx plus delta p delta y dy. That's the dp, and then we wedge that with dx. And then we have delta q delta x dx plus delta q delta y dy, all wedged with dy. And now if we distribute these through, I get delta p delta x dx wedge dx plus delta p delta y dy wedge dx plus delta q delta x dx wedge dy plus delta q delta y dy wedge dy. And notice the dx wedge dx and dy wedge dy are 0, so those go away. So I get delta p delta y dy wedge dx plus delta q delta x dx wedge dy. And now if we change the order of the dy and dx here, I get negative delta p delta y dx wedge dy plus delta q delta x dx wedge dy, which is exactly delta q delta x minus delta p delta y dx wedge dy. And that should look pretty familiar. If we look above, that's exactly what was showing up in our surface integral there. So if we take the left-hand side of Green's theorem, that's the integral over c of just omega, right? So our omega is this p dx plus q dy, which is exactly what we had there. This was omega. And now we see what we're integrating on the inside there is just d omega. So this is just the integral over S of d omega. So this is Green's theorem in terms of differential functions fields, differential form fields. So you can kind of see this is a much nicer way to write this. It's much easier to remember, and it goes along with what we said before. So when we talked about Stokes and Green's theorem before, one of the things I told you was we could think of this part here as this is like a derivative of f. And we mentioned this in the previous section, talked about this in terms of the exterior derivative. So that's exactly what we have here. The integral over the derivative of a one form field over the surface is the same thing as the integral over the one form over the boundary curve. So that's a really nice way to write Green's theorem. We're going to see this fits really well with all of our other situations for kind of our major theorems for our vector calculus. Okay, so let's move on to general surfaces. So now on to integrating two form fields over surfaces in R3. This is going to be a little bit more complicated. So let's start with thinking about what kind of surfaces we're going to look at. So we want our surfaces, just like we did with our vector field integrals, we want our surfaces to be parameterizable. So S given by, say, R of uv, so that u and v is in some region, say d, and r squared. So what this looked like for us in terms of pictures is we can think of working here in the uv plane, and then over here we're going to have our surface in 3 space. So what we can think of here is we've got some region here. This is our region D, and this maps onto some surface over here, S. Right, and so for any particular point, say UV, we're going to have a point over here given by, this is R of UV. So that's what we meant by our parameterization. But now we're going to want to think of the orientation here too. So I can take the vectors here. So think of this as u hat and v hat. So the vector of unit distance in the u direction and the vector of unit distance in the v direction. So you also still write these as I and j if you like to. So when I map this over here, if you remember what that mapped to was this mapped to the partial derivative of the vector parameterization in terms of u and the partial derivative with respect to v. And those gave our tangent vectors there. And so if we recall, well, if I look at the magnitude of Ru uv across the magnitude of Rv uv, this gave me the area. If I form like a little parallelogram here, and I look at that, it's not quite on the surface, but it approximates the surface well. So this gives the area of the parallelogram spanned by R of u, uv, and R of v, uv. And now, for us, what we're going to want to look at is we want to calculate that area as well. And so if you recall, what we did to do that is we wanted to keep track of the orientation as well. So our area form was dx wedge, or dy wedge dz plus dz wedge dx plus dx wedge dy. So that was our area 2 form. And now we want to plug into this. Well, to get the area spanned by those 2 vectors, we should plug those vectors into this area form. So this gives the signed area of the parallelogram spanned by Ru uv and Rv uv. So if you recall, when we were doing surface integrals before, there was always the question when we got to the surface integral part. Remember when we took this integral over s of f dot ds and we looked at the parameterization, we integrated over d and we looked at f of r of uv dotted with r of u cross r of v, and then we had the dA, and there was always this question that we had to deal with about, do we want this version or do we want to switch the order to get the other version? And we always calculated that and then we decided which one and we used that. So how does that correspond to above? Well, in this version up here, we switch the order of these. If the orientation is wrong. So we'll see an example of that in a few minutes, but that's just switching the order there is the same as switching the order of the cross product in the vector field form of this. So how are we going to define our integral then? Well, if I want to integrate a 2 form, so say omega, so this is a 2 form field. How I'm going to do is I'm going to integrate this over the region D. I'm going to take my 2 form field, and now I'm going to evaluate it at the point R of uv. So again, think of this as a point. Again, so a bit of abusive notation there. And now when I evaluate at that point, that means this part here is now a 2 form. So a 2 form inputs 2 vectors. So we're going to take R of u and R of v as our 2 vectors. And then we just have dA in the xy plane, or in the uv plane. So that's how we're going to define this. So let's do a silly example to start with and redo our example from before that's in the xy plane, just to see how it works in this case. And then we'll do a little bit more complicated example after that. So let's redo the example above. Okay, so if you remember in that case, we had omega is x squared y dx wedge dy, and our surface S was just given by this triangle here, where this was y is equal to 1 minus x, and this was our S. So this is pretty easy to parameterize. We could just stick with x and y, but let's go ahead and make it so it looks like what we're used to. And then there's no k component, so this is just 0k. And then my region D is just S, which we could just write as uv, so that 0 is less than or equal to u is less than or equal to 1 minus v, and 0 is less than or equal to v is less than or equal to 1. Now, if we take our partial derivatives, R of u is just I, and R of v is just j, so that's pretty easy. So now, let's go through our steps. So if we look at our definition here, the first thing we want to do is take our 2 form field and evaluate it at R of uv. So our 2 form field here is x squared y. So omega evaluated at R of uv. So we're going to replace the function in the front. The x's will become u's, and the y's will become v's because of our parameterization here. So I'm going to get u squared v, and then we still have the dx wedge dy here. And now I want to evaluate this at R of uv, R of u, R of v, and so this is u squared v, and then I want dx wedge dy of R of u, R of v, and so this just picks out, well, the dx takes the I component of each vector, so 0 and 1, dy takes the y component of each vector, so 0, 1, and then take the determinant of that, so this is just u squared v. So in this new language, the integral over omega is just the integral from 0 to 1, integral from 0 to 1 minus v of u squared v dA. And this is exactly what we had before, same integral as before, we just switch to u and v. So we get the same thing. This just kind of goes through how the language works in terms of evaluating the 2 form at the parameterization and then evaluating the dx wedge dy. So same thing, just in our new language. So you see it works the exact same in terms of the new language. So now let's go ahead and try a little bit more complicated example. So let's consider the differential two-form field. So I'm going to take this to be omega to be x dy wedge dz plus y dz wedge dx plus z to the fourth dx wedge dy. And let's calculate the integral over s of omega, where s is given by the cone z is equal to square root of x squared plus y squared beneath the plane z equals 1 with downward orientation. So the first thing we'll do is we're going to parameterize our surface. So this is an easy one to parameterize. So we can just take x to be u, y to be v, and then the z component then is just u squared plus v squared k hat. And what is our region D? Well, we just want the u and v's. Now, to get all of these pieces on the cone, we want u squared plus v squared to be between 0 and 1. So this is the same type of parameterization we did when we used vector fields. There's nothing new about that part. Now, if we evaluate our two-form field at uv, at r of uv, this is going to be u dy wedge dz, right? Because the x component, the I coefficient of our uv is u, and so that means we replace this x here with u. And then for the next term, we're going to replace the y with v. And then finally, for the z, we're going to replace it with square root of u squared plus v squared. So this just becomes u squared plus v squared to the 1/2 all raised to the 4th dx wedge dy. And if we simplify that a little bit, so when I take the square root to the 4th power, I just get squared. So I get u squared plus v squared squared dx wedge dy. So this is now our two-form. So next step is let's look at r of u. So this is going to be I plus u over u squared plus v squared to the 1/2 k. Okay, so just look up here at this, just take the derivative with respect to u. And similarly, we r of v is j plus v over u squared plus v squared to the 1/2 k. Now, we need to determine our order here, so we need to make sure our orientations match. So if I were to look at these vectors as RU cross RV, the K component is 1. But with our cone, we said we wanted downward orientation. So that means our unit vector should look like this. So we want negative K component. So that means we want to input not RU, RV, but RV, RU in that order to make sure our orientation matches up. Okay, so then let's go ahead and see what we're looking at. So this should be the integral over our region D of omega of r of uv, and then to make sure our orientation is downward, we need RU, or RV comma RU, and then we want this in dA component. So next thing we need to do is evaluate this. Well, what we're going to do is we look at omega of r of uv, and then we input r of v, comma r of u. And so we have u, and then we have dy wedge dz of r of v, r of u, plus v dz wedge dx of r of v, r of u, plus, and then we had u squared plus v squared squared, and then dx wedge dy r of v, r of u. And so if we just write down the definition here, this is, remember, the dy is taking the y component of these. So the y component of r of v is 1. The y component of the j component, I should say, the j component of r of v is 1. The j component of r of u is 0. And then the dz is taking the z component. So maybe I need to write this a little bit bigger here. So I get a 1 and a 0, and then I get the k component of r of v is u over u squared plus v squared to the 1/2, and the k component of r of u is u over u squared plus v squared to the 1/2. Take the determinant of that, plus v, and then we have the determinant. In this case, we do dz dx, so it's v over u squared plus v squared to the 1/2, u over u squared plus v squared to the 1/2, and then we take the x component, which is 0 and 1, and finally u squared plus v squared, and then the x component of rv is 0, the x component of ru is 1, 1, 0. So now take these determinants, so this is u times u over u squared plus v squared to the 1/2, plus v times v over u squared plus v squared to the 1/2, and then plus u squared, this should be squared, u squared plus v squared squared times 1. And if we simplify this, this becomes times -1, sorry. This determinant here is a -1. So this becomes u squared over u squared plus v squared to the 1/2 plus v squared over u squared plus v squared to the 1/2 minus u squared plus v squared squared. So combining these first two terms and simplifying, this is u squared plus v squared to the 1/2 minus u squared plus v squared squared. So finally, we can now evaluate the integral. It's the integral over d of u squared plus v squared to the 1/2 minus u squared plus v squared squared dA. And remember, d is just the region inside the circle here of radius 1. So this definitely looks like polar coordinate type integral. So this is the integral from 0 to 2 pi, integral from 0 to 1, and I have r squared to the 1/2, so this is r minus r to the 4th, r dr d theta. And so this becomes, if we evaluate this integral, this ends up just being pi over 3. So not a difficult integral, just do a little work there to work that out. So how does this relate to what we did before with vector fields? Well, what we could do is, if we wanted to calculate the flux, remember we looked at if we had some vector field f of x, y, z, so in the previous example, say, we would have written this. This would have been our vector field. And so what we would have done is just taken that vector field, remember, that came from, or the two form that came from the vector field, the flux form. So this would have been just x dy wedge dz plus y dz wedge dx plus z to the 4th dx wedge dy. So this is exactly what we just did. So what we had then was, so the integral, how we would have done it before with f dot ds, is exactly the integral over s of this two-form field, which is what we calculated. So we're not really getting anything different there. It's just a different language to work with. Okay, so let's rephrase Stokes' theorem. And this is not going to be too complicated based on what we've already done. So remember, Stokes' theorem said if we look at the line integral around C of a vector field F, this was S, and then we had the curl dot ds, and we just had to make sure the orientations matched. Well, let's think about what each of these things are. So we know f dot dr, this is exactly the integral over C of this one form field that comes from the vector field F. And we know from our section on the exterior derivative that the derivative of this one form field is exactly the two form field that comes from the curl of F. So what we're saying here then is Stokes' theorem would say the integral over C of omega F1 is the integral over S of the two form field coming from the curl of F, which is the exact same thing we just said as DF1. So once again, we can rewrite Stokes' theorem, and this looks exactly like Green's theorem now. Integral over C of omega is the same thing as the integral over S of d omega. So this is Stokes' theorem in terms of forms. So we have one more integral to do, and that's triple integrals. So what about three forms? Well, remember our volume form is just dx wedge dy wedge dz. And so for any three form field, well, that just looks like omega is f of x, y, z dx wedge dy wedge dz. So pretty easy to decide what we're going to do this. If we have a region E, omega should just be the integral over E of f of x, y, z dv, because that dx wedge dy wedge dz is just our volume form. So now so there's nothing really that interesting there. It's just, again, new language, but it isn't really giving us much new there. So what about the divergence theorem? So the last thing we saw in terms of our major theorems, well, remember what that said was that if I integrate a vector field over a surface S that's a closed surface, this is the same as the integral of the region E of the divergence of f dv, where S is the boundary of the closed region E with outward orientation. So that was our divergence theorem. Well, let's think of how we can rewrite this. So let's let omega f, this is the two form field, from F. And now what we calculated in the section on exterior derivatives was if I take the derivative of this two form field, this just became the divergence of F dx wedge dy wedge dz. So in particular then, if I take the divergence theorem, I can write this as omega integral over this two form field, which the divergence says this is the same thing as the integral over E of this, which we said is the integral over E of dx wedge dy wedge dz. And now note this is exactly the integral over E of d omega f2. So once again, divergence theorem, rewriting this can be written in terms of forms as just the integral over s of omega is the integral over e of d omega. So it's kind of nice to see. I said during the regular lectures of vector calculus that all of these different major theorems were saying if you took the derivative of something over a region and then integrated that, it was the same as the integral over whatever the original thing you were integrating over the boundary. So in this case, we could take d of omega, integrate it over whatever our region is, whether it's a curve or a surface or a volume, and then it would just be equal to the integral of omega over the boundary, whether that boundary are 2 points, a curve, or a surface. So we can see with forms, we came up with a new language to work with all of this stuff that came with an orientation, and a lot of the things make a little bit more sense now, hopefully, in terms of where the divergence, the curl, the gradient, all of these things kind of come up naturally when you're working with differential forms instead of just vector calculus. And then we see all of our major theorems fit the exact same pattern and look the exact way when we write them in terms of differential forms.